Good
Okay.
morning, good evening, everyone, and welcome to the latest edition of SETI Live. My name is Simon Steele. I'm the Deputy Director of the Carl Sagan Center here at the SETI Institute in Mountain View, California. And a huge 9 hours time difference away is our special guest. I'd like to welcome Dr. Paula Sánchez Sáez from the European Southern Observatory. And we're going to talk today about one of my favorite topics, which is supermassive black holes in galaxies. Turns out most, if not all, galaxies have supermassive black holes at their centers. Some of these supermassive black holes are just sitting there doing not much at all, including our one in our Milky Way. And some of them are just going insane. They're giant Death Stars like the ones in M87 in the Virgo cluster. But what changes one from another? What awakens these sleeping giants? And that is the topic of the conversation, because Paula and her team has found one of these supermassive black holes potentially waking up. So Paula, welcome.
Thank you.
For everybody, please, let us know where you're tuning in from. If you have any questions, just pop them into the comments and we'll get those questions out to you. Paula, you are originally from Chile.
Yes.
You work from the European Southern Observatory, and you're now based in Germany, which is not southern at all. Can you tell us a little bit about the structure of ESO as an organization?
So ESO is basically this organization that groups many countries from Europe mainly, but also other countries from other continents, mostly European countries, but it's called the European Southern Observatory because all the telescopes are in the south. So basically in Chile. At the moment, all the telescopes are in the Atacama Desert in the north of Chile. But the reason is because there you have the best sky conditions to observe. Particularly, you have access to the nucleus of the galaxy, so the bulge, and also you have access to the Magellanic Clouds that are not visible from the north. So it's a very good site to get observations that are not easy to take from the north, but also the conditions in the Atacama Desert are incredible. So ESO has this structure of many member states. They contribute and support the observatory, and then Chile is the host member that has basically all the telescopes.
Right. So so you're building these telescopes in the middle of the desert at high altitude. So it's very difficult to get to because you have the most incredible skies down there, don't you? And and also some of the biggest telescopes in the world. What's the biggest one you have?
So now the biggest one are the VLTs. So those are 4 telescopes with around 8 meters each one diameter. But they can also work together as a big telescope of around 16 meters. But this is the current state. In the next decade, we will have the extremely large telescope that will have almost 40 meters, 39, let's say. And it's going to be the biggest telescope ever built by the humankind. And it's going to be a whole revolution.
Right. The ELT. Astronomers have very wonderful ways of naming telescopes.
VLT is for very large telescope, and then ELT is for extremely large. So let's see what is the next name.
Yes, indeed. They're going to run out of those sort of terms soon. But that's very exciting. So your work, you have studied galaxies and the black holes at the centers of galaxies. And back in 2019, your team made this discovery around this galaxy, which has the, again, a very romantic name, SDSS 1335 plus 0728. I'll let you explain what that name means, because that says a little bit about the galaxy in itself.
But this basically the name is basically the coordinate of the source.
It's just the coordinates, isn't it? Yes. Yeah. No good name for that. Maybe it'll get a name. And SDSS, of course, stands for the Sloan Digital Sky Survey, which was originally discovered. Maybe we can bring up an image of the galaxy. This is it. SDSS 1335 plus 0728. It's the yellowy smudge in the center. The bright star in the top. That's one of our own galaxy stars getting in the way. What sort of galaxy is it, Paula?
Sorry, can you repeat the question?
Yes, what sort of galaxy is it?
So it's from the image, it's hard to tell because this galaxy is super small, but we believe it's like a spiral galaxy, but not with many star formation, like a very boring galaxy. But something interesting about this galaxy is the stellar mass, which is not super large. So that's why it got our attention, because normally we don't know many galaxies with masses lower than 10 to the 10 solar masses with active black holes. And if you find galaxies with masses smaller than this, with active black holes, that's super important to understand how these galaxies evolve and how they form, because we know that there is some connection between the black hole and the galaxy. But it's not clear yet what is this connection, and we need to understand the connection at the low end of the mass distribution.
Right. Now, our universe has billions of galaxies. Some of them are big and beautiful. Some of them are little sort of smudgy blobs. Yeah. This one, as you say, is not a particularly interesting one. How did you all find out that something was interesting going on when you've got all of these galaxies all over the place? What caught your eye, and how did it catch your eye that something was happening in this very ordinary galaxy?
So I guess you know about the SETI Transit Facility, this telescope that is based in the Palomar Observatory in the US. So it's a telescope that is making a survey of the whole north sky. So it's observing more or less every 2 or 3 days, and it can generate time series of data. So you have for each object, you will have like a time series where you have time and the amount of light, so flux or luminosity, and then you can study if the source evolves with time or if it's constant. And in this survey, they have a very interesting data set that is called the alert stream. So the alert stream is generated whenever you have a change in the images. And they have a reference image, and then they compare every new observation with this reference image. And when there is a change, they report an alert. And there are a system that is called alert broker. There are several of them around the world that are connecting to these alert streams and are classifying this data using machine learning or artificial intelligence. And one of these brokers is called Alerce, and it's based in Chile. And I did my PhD there and also my first postdoc. So I was working with the Alerce team at the time. And we developed a machine learning model that was classifying the objects according to these alerts. So basically, we were checking, okay, the evolution, if it's more or less a transient event, or if it's constant, or if it's periodic. And then using different attributes and machine learning, we created this classifier. And among the classes that this classifier was classifying, we have AGNs. So what I did was, okay, I was interested in looking for AGNs in these small galaxies. AGN means active galactic nuclei, or a black hole that is active, accreting material that produces a lot of light. So why? Because as I said before, finding AGNs or active black holes in small galaxies can help us to understand how was the formation of supermassive black holes. Because we have to go from something that is a stellar black hole to a supermassive black hole. How do you go from something very small to a very huge black hole? It's not clear yet. And we know that the answer is probably in these small galaxies. So I was trying to use this machine learning technique to find small AGNs, and then this source appeared. And at the beginning, I thought it was a normal source, because if you see the time series or the light curve, we call these light curves, this time series of time versus light, it was like a normal AGN, like a classical AGN. But then I noticed that if I went to archival data and look how the source looked like several years ago, it was not varying at all. It was a constant galaxy. Like, okay, you have to think that normal galaxies without active black holes, they don't vary. They have always the same amount of light. While AGNs, active black holes, they vary in time. So you see that the light curves are not constant. They are we call it stochastic, but it's basically a random variation that has a time scale of a few hundred days. And we noticed that this source was also showing those variations, but 20 years ago, it wasn't doing the same. So then we were, this is tricky, because it's like how this source passes from being super normal and constant and non-active to something that is now doing crazy stuff. And then after we noticed that, we started the follow-up campaign with different facilities. So we applied for telescope time in different telescopes, mostly in the south, because of my connections in Chile. I was using Chilean telescopes, but also in the US, and also space-based telescopes. And after all this campaign, the conclusion is that probably what we are seeing is the awakening of a black hole. That could be because it's a newborn agent. That means we know that all these galaxies that are active have a supermassive black hole that is actively accreting material, but we don't know how they pass from being passive to being active. And this could be the first time we see this transition. But also another option is that we are seeing a new class of object that we haven't seen before, because now it's unclear if the properties we observe in this object are all associated to an AGN-like object or a new class of object. That's the mystery that we're trying to solve now.
Okay, we'll come back to that in a second. And yes. Just like to welcome people who've tuned in. We've got Stephen from North Carolina. We got people from Central New Jersey, from Germany. Julia, welcome. We've got, and sorry if I miss your name as I scroll down, we got people from tuning in from Australia, Niagara Falls, Illinois, Maryland, Michigan, Stafford in the UK, and Colombia and Northern Maine. So welcome everybody, and thank you. We've got some questions coming into the chat now. So you've got this pretty ordinary galaxy. It has a supermassive black hole at the center, like all galaxies do, pretty much. So that's nothing strange. But suddenly, using machine learning and monitoring of thousands of galaxies, you notice that something's changing here. And that sends out an alert, an electronic message that you and other astronomers will see, and you say, "Oh, this is interesting. Let's look at how this is varying." And from that, you can then request time to say, "Let's look at this galaxy with different telescopes." And are you looking at it with different wavelengths as well? Are they optical and non-optical telescopes?
Yes. So the strategy we followed was, whenever we got an observation with an optical telescope, we requested observations in the UV and in X-rays with Swift. Mm-hmm. And the curious part was that for several years, the source wasn't showing any emission in the X-rays until February this year. February this year, we noticed the first detection in the X-rays. And now we are still monitoring the source in the X-rays because it's still doing interesting things. It's a work that we are about to submit soon. It's an ongoing work, so I cannot tell you much about it. But in summary, it's more interesting than what we believe. And it's this paper that we just published is the first one of a series of papers that we hope to publish, because this source is evolving now. So it's something that is happening in human timescales, and the idea is to keep monitoring and report all the new activity it shows.
Right. So this is maybe let's talk a little bit about what we mean by an AGN, or active galactic nucleus. And all of this is happening right at the core of the galaxy. Galaxies are huge, cities of stars. This is happening more on sort of solar system size scales, isn't it? Can you talk a little bit about, first of all, how big this supermassive black hole is and what's happening around it, and what you think is changing around this particular one? And I know there's an illustration that we can pull up to give a view of what we think is happening.
Yes, so this is an illustration that the ESO science communication team created. It was amazing for the press release that we had with ESO. So basically, we know that AGNs are the supermassive black holes that are surrounded by an accretion disk. That means it's a disk of gas that is being accreted by the black hole. And in this process of accretion, there is a release of a lot of light and energy. This is basically because of the high gravitational potential of black holes. Like as soon as you move a little bit closer to the black hole, the release of energy is huge. That's why these accretion disks are so bright. And in the case of this source, it's not clear yet what produced the feeding of the black hole. Like this is something we want to explore with more data. Hopefully we will get the data. But one of the mysteries is why now we have an accretion disk, while a few years before there was nothing. This is something that has been trying to understand for several years. Like people are trying to understand what feeds AGNs or supermassive black holes. Maybe this source will help us to understand. So what we know now is that basically we have an accretion disk. That's because we have the optical and the UV behavior that is super like close to what we expect to see from a normal AGN. But then there are other properties that we don't see in this source that are normally associated to AGNs, like a structure that is called the broadline region. This is a set of clouds that are orbiting the accretion disk, but that are not part of the accretion disk. And these clouds produce something that we call the broadlines in the optical spectrum. And we haven't seen those broadlines yet. But what we see now is narrow lines in the optical spectrum. And those lines are produced in a more external region of the system. But it's still very small compared to normal AGNs. We know that this narrow line region in AGNs is very extended, several lights of years, thousands of lights of years, while in this case it's a few lights of years. It's like only 3. So that's also unexpected for this source. And it's the first case where we see this kind of behavior. Also, in the X-ray emission, what we believe that could be happening is that there is a star that is orbiting this system that is crossing the accretion disk and is producing some X-ray emission in the process. This is still under study, but it's one of the possibilities. Also, we know that normal AGNs have a structure called the corona that is emitting the X-rays. That's also another option, but we don't see the normal properties that AGNs with a corona present. So yeah, this also something important also from AGNs. Normal AGNs have a dusty torus that is surrounding it's like the biggest structure in an AGN. And now after 3 years, we saw the evolution of the source in the mid-infrared, using the WISE telescope. And that means maybe now the dust that is surrounding this system is forming a dusty torus structure, or the dust that is farther away is reacting to the activity in the nucleus. So we still need to see how this evolves to conclude what is going on. Another option is that all this structure that was formed comes from a transient event, like a tidal disruption event, where you have a star that is disrupted by a supermassive black hole. But this is an event that normally lasts only a few hundred of days, while this source has been varying for almost 5 years now. So it can be super hard to explain this with a normal tidal disruption event. So what we believe is probably this is either an AGN that is just being formed, or is a new class of transient object that we haven't seen before. These are the 2 options. In any case, it's very interesting.
So that image there, what scale is that? We're looking at a dusty torus ring surrounded.
So here, what we try to show is the accretion disk, and then the fluffy structure around it could be the torus. But basically here, the physical scale is of the order of the solar system.
Okay.
Of the accretion disk. This is something we need to measure, of course, because this is although it's a supermassive black hole, it is a small supermassive black hole. Normally, most of the known supermassive black holes tend to have masses of around 100 million solar masses, while in this case, it's around 1 million solar masses. So it's a very small black hole for a normal AGN. So probably the scales here are smaller, but that's something we need to measure with. There are several techniques that we can use to measure the size of the accretion disk.
Right. So this is not necessarily a supermassive. This is a pretty good massive black hole.
Yes.
It's around 1 million. That's slightly smaller than the Milky Way's own supermassive black hole, isn't it? And so certainly very small compared with quasars and things like that.
And that's something actually that we need to measure well, because now we have an estimate from the host galaxy. So we have this connection between the mass of the galaxy and the mass of the black hole, and we use that to estimate the mass of the black hole. But as we don't have all the normal properties that we see in AGNs, it's hard to measure the black hole mass directly. So we want to obtain also new telescope data to measure basically the black hole mass properly.
Right. Because black holes, as we know, are sort of black and invisible when they're on their own. It's very difficult to find a black hole if there's nothing close to it that sort of suggests its presence. And as you say, this one it seems as though it was quite isolated in itself. And now it's being fed by some process that seems to be more than just a poor unlucky star that's got too close to it. There's something much more substantial and much more consistent that's falling on to the black hole, and that will give you much more of an idea of the parameters of the black hole itself.
Yes, so that's something interesting, I think, is that we can see this source evolve in real time, like in human timescales. So yeah, let's see what happens in the next years.
And it always amazes me, of course, that supermassive black holes, AGNs, are the brightest things in the universe, and yet a black hole is the darkest thing in the universe. It's this sort of a paradox. The black holes are the brightest things, and of course that's due to the material falling onto the black hole rather than the black hole itself, which is really cool.
Yeah.
So we're going to go to a couple of questions in a second. I just want to go back to this two things. One question is, could it be something else going on? And the other one is this linkage between supermassive black hole evolution and galaxy evolution. What the relationship between a black hole and a galaxy is, because these are tiny compared to galaxies, and yet they seem to have a very, very close symbiotic relationship with their host galaxy.
Yes, that's actually one of the big questions now, and I think the James Webb Telescope is helping us to understand, because now we have many candidates of AGNs at very high redshift, so very distant, at very long distances. And I was the other day attending a talk here at ESO. No, it was at MPE, the Max Planck Institute, where Luis Ho was talking about the discoveries from James Webb. And he was saying that now people believe that maybe the very old ancient black holes were formed first, and then there was a galaxy that formed around it. But this is something, it's a speculation, we don't know yet. And it's something that I hope we will understand in the next years, thanks to the James Webb Telescope, and in the next years with the ESO ELT. It's one of the open questions, like why we know there is this connection, but we don't know yet why. It's very rare, as you said. It's a very small structure that has the size of a solar system, and then you have the whole galaxy that is huge, and somehow they are connected. So yeah, maybe it's because black holes are formed first, and then you have all the material coming around. Maybe it's something that we don't know. It would be nice to see this answer finally answered in the next, this question finally answered in the next years.
Yeah, cool. Okay, gonna pop over to some of these questions. First one is from Stephen. Do we have an understanding of galaxies that do not have supermassive black holes? Do we have an actual list, or is it too numerous to count? So supermassive black holes, does every single galaxy, are there exceptions?
So we know that for masses larger than 10 to the 10 solar masses, all of them must have a supermassive black hole. For masses lower than that, we don't know yet. And that's why we need to study them and trying to find, there are different ways to identify a black hole in a galaxy. One way is to identify an AGN. Another one is to detect transient events like these tidal disruption events, or TDEs. Other option is to measure very well the the stellar dynamics around the nucleus, but that's not super easy now. So it's an open question now. What is the occupation fraction of supermassive black holes in all the galaxies? That we know that for this 10 to the 10, beyond that, it's well known that all of them have black holes. But then for lower masses, we don't know yet. And we know that depending on the formation mechanism of supermassive black holes, we will expect to see different fractions of galaxies with black holes in this mass regime. So it's super important to understand that. It's one of the big questions now.
Cool, thank you. So, question from Doug: is the light increase in every wavelength and enough to kill every living thing in the galaxy?
Ooh.
All right, so there's going back to a Death Star question.
Yeah, so that's hard to tell. I haven't made the math, but I will say probably the emission is not like, if there is a planet with life very close to the black hole, probably, yeah, the life there is gone. But most of the emission comes from the nucleus. Like if you see if you take an image of the whole galaxy, you will see that most of the emission is dominated by the galaxy itself, not this new activity. So with respect to the galaxy, the source is very faint, like the AGN itself is very faint. So I will say that probably no. If there is a planet in the outskirts of the galaxy, probably the life there is still there. But yeah, it's something hard to answer.
Yeah. Everything is fine as long as you're quite a distance away. Yeah, good. I'd just like to call out Julia. Thank you for the stars on Facebook. Thank you very much for listening and tuning in. So a question from Jonathan, linking this. He asked about any links to gamma ray bursts, and that's what sort of, how does that compare? And also, has this been measured? Did you mention in gamma ray? And I apologize.
No, we don't have any gamma ray detection at the moment. Maybe that's one of the mechanisms to form gamma ray bursts. Like, we don't know yet what produced these bursts. So yeah, but at the moment we know from this source, at least there is no report. There is no single report of a gamma ray detection.
Okay. And actually, Stephen asked about neutrino observations, and
yeah, we don't have any detection yet.
Yeah, it's probably a little bit too far away, isn't it? I imagine, for the flux on that, but yeah, potentially. Okay, let's see. We've got a couple more questions. Question from Manav. How much of the process is automated versus manual calculations? You mentioned machine learning. Are poor humans being cut out of this whole?
So basically, most of the pre-filtering is done with machine learning, but then the identification was done by a human, like it was me, basically. So the machine learning algorithm gave me the candidates, and then it was like my first list was a list of 35 objects with interesting activity in these dwarf galaxies, like small galaxies. And then I was checking one by one, and then I found this. That was the most interesting one.
Okay. So
yeah, it's a mix.
It's a mix, yeah.
But then machine learning helps you to remove the whole set of contamination. Like, imagine if you have to do this for every single galaxy. There are millions of known galaxies with low masses. So imagine having to check each one of them. So at least my list reduced, I think, my original sample had around 300,000 objects that I knew were low mass. And then the list reduced to 35 candidates. So then it was more manageable.
Yeah. It really is revolutionizing the way that you can do analysis on so many galaxies. I know in the old days, and I remember the old days, your surveys had to be very, very small because you just did not have that ability to do an analysis on so many galaxies. So we're coming to the end of time. I just want to pull up Stephen's questions about the accretion disk. over or around an AGN, around the black hole, would these have been built up over thousands or millions of years? And I think what you're saying is that you are seeing the construction of this accretion disk.
Yes. So something we need to find out yet is whether there was some evidence of activity very close to the nucleus. We know that from we don't have IFU images, like you know this. You have these images for which in every pixel you have a spectrum. We don't have this kind of data yet, but we have the normal fiber spectra or long slit spectra. From those, we know that there is no evidence of previous activity, but we need these very detailed observations to confirm that. So maybe there is some evidence of other sources where they saw some kind of activity that was dropped off at the end. So now it's not anymore, but that, let's say a few thousands years ago, there was something there. So the idea will be to try to see the same kind of behavior in the very central part of the galaxy. But we know that this increase in activity happened in a few months. That's the only thing we know. Like unfortunately, there is a gap in the data. Like we have this amazing time series, but when this source become active, the source was not visible from the Earth. So we don't know what happened in the 4 months before the end of 2019. It could be that maybe in November or October the source became active. We don't know. It's impossible to know now. But it was a very rapid event, and that's very puzzling because it's like you will expect these sources that are huge to evolve very slowly. But we know from evidence from other classes of objects that are called changing look AGNs that these events can be faster than we expect. So yeah, it's something we need to answer. We need the data. So I'm applying for telescope time. If there is an astronomer around, please give me the time.
Thank you. And actually, that leads me to my last question. And thank you, everybody, for giving your questions and comments. Sorry, we can't get to them all. What next? Are you going to continue monitoring SDSS 1335? Is that going to be a lifelong companion? Are you going to be looking for other types of galaxies that are very similar to that?
Yeah, so my plan is to continue monitoring the source using different facilities. That's the plan. Now that the source is known in the community, I hope I will get the time because it's a very competitive field. So let's see. But then also, now that we know these kind of objects are around, the plan is to still look for more of them. I'm sure there will be more, especially with the Vera Rubin Observatory that is going to start operating next year in Chile as well. Probably we will have many candidates in the next years. So let's see.
Good. And so we will be inviting you back in a few years to hear what's happening, especially with our old friend now, SDSS 1335. Excuse me. Thank you very much, Paula, for joining us today. Thank you very much, everybody, for tuning in. This is a production of the SETI Institute, which is a non-profit organization. So please do visit our website. We appreciate donations to keep the exciting science running and keep these shows talking to the cutting-edge astronomers of the world and bringing you the science and what's happening right now. So thank you, Paula. We will see you again soon. Thank you, everyone, for tuning in. And we will see you on the next SETI Live. Take care.
Bye.